Okay, so I kept searching around online, and then I found this website, which has pretty much the algorithm coded up perfectly. So I don't, I don't. I was thinking of doing something with the homework, but I don't know what I'm going to do because the answer is right here. So, um, but I wanted to talk about, an important part of this solving the, the cipher and, trying to decipher the text. A very important part is figuring out the probability of the resulting decoding, right? And we want to take steps in a way that maximizes the probability of the text that we see, right? Um, so again, we're talking about our classical substitution cipher. And all we're doing is we are just saying, the letter A now goes with the letter M, and the letter B goes with some other letter, so on and so forth. Okay, and we need to be able to evaluate the probability associated with a proposed kind of cipher key. So we propose, I think the letter A corresponds with the letter K instead of the letter M. And we want to say, okay, well, does that change the probability of the text that we're looking at? And we want to test that out. So we need to measure that probability. Okay, and in the reading that I gave you, there were a couple methods mentioned. In the machine learning for hackers, the author uses a lexical database, and that one it's a listing of pretty much every single word in the English language, and it says, the probability of seeing the word A is quite high, and the probability of seeing the word the is also pretty high. The probability of seeing some other word is much lower, and things like that. So, the author there has a lexical database. He doesn't specify where that lexical database came from, and so it's we just kind of have to say, okay, well, that's fine. The other authors talk about using a reference text, such as War and Peace, okay? And so I wanted to show how we would use a reference text to create, kind of a probability table. And effectively, what we're going to do is we're going to build a transition matrix from one letter to the next letter, okay? So, we will build transition matrix showing, for basically for going from one letter to another. Okay, and so the way we're going to do this is we're going to have, it's going to be a 27 by 27 matrix. Okay, and we're going to start off, I'm trying to remember whether the first letter, we go A, B, C, D, all the way through X, Y, Z, and then basically a non-alphabet thing. Okay, so if it's a number, if it's a symbol, if it's something other than A through Z, we're gonna just classify it as a non-alpha over here. and then I don't know, maybe on the actual thing it goes the other way, but A, B, C, dot, 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 all the way through, X, Y, Z, and then non-alpha. And basically, this is going to be kind of our first letter, and then over here, this would be the second letter. And so, this is what we would expect to see. There's probably not very many words where you're going to see the letter J followed by the letter Q or something like that, okay? So J, Q, that combination, J comma Q, we expect to have, something like 0, okay? Meanwhile, there's going to be, every time you see the letter Q, almost certainly it will be followed by the letter U, and so we expect this one to be very close to 1, something like 0.999, okay? Because every time you see the letter Q, and I said, predict what letter comes next, we expect something like that, okay? And so, I have some code. What we're going to do, and this is code written up by someone else, so I can't take any credit. Basically, we're going to give it a reference text, okay? And what we do is we say, okay, we're going to start right here. And actually, so the first, we start off with kind of a blank thing. And then so what we're going to do is we're just going to tally up how many letter pairs we see. Okay, so we first start off with a blank, and then we see a W. Okay, and so in that case, blank to W will get a tally of 1. Okay, and then we say, okay, now my current letter is okay, the last letter I saw was a W, and then the next letter is an E. And so we're going to go to, the row W and the column E, and we're going to tally a 1 there. Okay, and then we go on, and then we say E followed by blank. Okay, and then we put another tally there. E followed by blank. We're going to put a tally there. Okay, and as it goes on, we go through the entire line, and then we go to the next line, right? And then we see the same, because the word we shows up at the beginning again, we would go, oh, okay, blank followed by W. Okay, we're going to change this from 1 to 2. W followed by E, we're going to add another thing, and we go on and so on and so forth, and we go through every single line, and we just keep adding tallies, saying how many times did we see this letter followed by this letter. Okay, and we go through our entire 27, or we fill out these numbers for every single thing in the matrix. Okay, and what we're going to do is we're going to use a big reference text, such as War and Peace. Okay, so this is, War and Peace has been translated into English. Okay, from Russian, and it's it's the plain text file is like several megabytes large. Okay, it's a really long. Where did it go? Okay, yeah, it's like 3 megabytes big. This is just the plain text, and this is coming from Project Gutenberg. So we'll just leave it like this. We're not going to bother trying to like clean this up and get rid of any of these weird the headings up here, and then and what we're going to do is we're going to just say, okay, the first letter here is this, followed by this letter, and go on through each line. Okay, and we just do this. Has anybody read through all of War and Peace? Yes, yes. Okay. It's long, and but considered one of the greatest works of literature, of all time, type of thing. But I have not read it, nor have I. But it will serve as a reference text here. Okay. And so let me open up our text code, and I'll just kind of walk you through the text thing. And so here we're going to load up War and Peace. And let me set my working directory here. Okay, so we're going to use the command read lines. Okay, you don't have to follow along, but if you do want to follow along, you can click this link for an R implementation of the MCMC cipher algorithm, and I've basically just copied the code that that Andrew Landgraf has written for us. Okay, so we load this up, and the plain text file has 66,000 lines, okay, in it. All right, and it's just a character vector, okay, and so in memory it takes 8 megabytes of space, and I can just say, okay, reference kind of the first element. There's some gibberish there, and so this is just a single character element, okay, and so it's just a character vector with 66,000, where each one is kind of several of these things. So if I just say, head, the first 6 lines of the text file is this, okay? And okay, and so what we're going to do is we're going to do to upper. We're going to just change everything to uppercase, and then so now we don't have to worry about case being an issue, okay? And then we're going to set up our transition matrix, okay? So right now we just have a blank 27 by 27 transition matrix. And then we're going to give our transition matrix some names, okay? Just some row names and column names. So rather than being 1 through 27, we will say, we check transition matrix, it's A through Z blank, A through Z blank, okay? And we're going to say, okay? And when we start off with using the blank character as kind of our first thing, okay? And then what we're going to do is we're going to say for each line, for line and 1 through basically 66,000, okay? Then, well, and then we just have kind of a, for every 1,000 lines, we're going to just have it print that it worked on, some line, because it's going to take a while to go through all 66,000 lines. And so if it's divisible by 1,000, just print out, which line you're working on, okay? So then for each line, we're going to look at each position by counting how many characters are in that vector element, right? So we say, so let's say our line is line 2, okay? Then when we subset reference line 2, we have this, and we can just ask number of characters in here. Okay, so there's 60 characters there. Okay, so we're going to go through each of these 60 characters, and then the current letter will be, we just do a substring of this. So if I do a substring starting off with the first letter, position is equal to 1. If I substring this, it's going to return the letter T. And if I say position 4, then I substring this, this will give me the blank, okay? And at position 5, then it'll be the letter P, right? Because we're looking at the Project Gutenberg, things like that, okay? And then so we just say, if the current letter is one of the, is an A through Z, okay? Then go to the transition matrix, and the row you're going to go to is the last letter that we're looking at, and then the column will be the current letter. So what's the probability of going from the last letter to the current letter? And what you're going to do is you're going to set that value equal to whatever value is in the matrix, and then you add 1 to it. Okay, so we're just adding tallies right there. Okay, and then set your current letter to be the last letter. Okay, and basically repeat. Okay, we have basically just kind of a special case if it's not in the uppercase, if it's not A through Z, and the last letter is not the blank space, okay? So then what you're going to do is you're going to go from the transit. Basically, though, it's the word ends with a certain letter, okay? And so you say you put an element in basically like from E to being blank, okay? So, what's the probability of ending with that letter? You put it right there. And then we have one last thing. When you reach the very end of a line of text, okay? So this part right here goes through the 60th character here, and then but we also want to, so this is going from O to Y, but we also want to put in like going from Y to ending the word, right? So that's taken care of right here. We say once you reach the end of a line of text, you're going to say that the last letter is now blank, and then you create a transition from going from whatever letter it is to the blank space, okay? And then you do that. Okay, so I'm going to just go ahead and run through this, and it will. Let me just run all of this, okay? And it's going to take a little bit of time, all right? It's just working through all 66,000 lines of War and Peace, and it will by doing this, it's going to establish our transition matrix, okay? So right now it's just tallying up how many times it saw us go from the letter W to the letter E. How many times did it see the going from, the letter K to the letter J, okay? That probably didn't happen very often, okay? Q to U will happen more often, I don't know. N to G probably quite often, something like that, okay? And so it's just working through the entire reference text. I mean, we could have used a different reference text. What are other really long novels? What, Moby Dick and yeah, okay, all these Russian novels that are super long and huh? Stephen King, yeah. Okay, I don't know how long that one is, but I guess it's long. Okay. East of Eden is not super long, but it's a little longer. But okay. This is probably not the audience for literature, right? There's a reason why we're. Anyone minoring in like a humanities thing?
Russian language.
Russian language. Okay. Anybody else? Poli-sci and. Okay. All right. Well. Okay, it's done now. All right, so let's take a look at our transition matrix. This is a transition matrix. Let's take a look. All right, and so we see, okay, this is just the counts. And so we see, okay, E shows up quite a lot. So, we go, there's a lot of words that end in E, okay? Whereas, Q to A, all of these showed up 0 times. And then looking at Q, this is the letter U, and then I guess a few words, there were 2 words that ended with Q, and so on and so forth. So this is our transition matrix of counts, and we want to see, okay, how often, what we want to do is we want to basically take the row sum for each of these, and then divide each of these values by the row sum. But what we're going to also do is, we're going to add 1 to each of these, so none of these will have a probability of 0, or at least a minimum. So we're going to just add 1, which will just make everything a little bit bigger. So we do transition matrix plus 1, and then this is a function called sweep. But basically, what I want to do is I just want to take the entire row total. So I'm going to do row sum of transition matrix plus 1. So it's going to add 1 to every element. Do the row sum of that. And then when it applies sweep, it's going to sweep using the division function. So it's going to take each thing and then go across and sweep by doing this divided by this. basically it's doing what we want it to do. Okay, so I do that, and then now I have probabilities associated with each of these things. Okay, so if I look at Q, everything has a very small probability, and then Q to U will have a very high probability, like 98%. Okay, and then these other ones, they have other probabilities, so on and so forth. Okay, and then we can plot this because this will probably be easier to understand if we plot. So I load up my libraries ggplot2 and reshape. Reshape allows me to do what's called melt, because in ggplot everything has to be in a data frame, and right now we have a matrix. So what melt does, it takes this 27 by 27 matrix and turns it into a whatever 27 squared is data frame. Okay, and then so it creates two columns. So it basically matches up. It says, coordinate 1, coordinate 2, and the value there is that, because ggplot needs the data in that form rather than you can't just give it a 27 by 27 matrix. Okay, so anyway, we do this, and let's take a look. And this looks exactly right. So here's the row Q. There's basically probability pretty much 0 for everything except for the letter U. Okay. And then we see, the entire column for E is pretty dark, meaning that E shows up after a lot of letters. Okay, it shows up, for the letter V. The letter V is quite often followed by E, sometimes by A, I, O, and blank, and occasionally by the letter N. Okay, and what letters follow X? X might be followed by A, C, E, I, P quite a bit, T, often V and X, I guess. All right. The letter Y isn't followed by very many things, but will often end a word. Okay. A lot of words end with D also. Okay, and things like that. And so we get a sense of what appears. Okay. Yeah, the letter Y comes after the letter L and R and B quite often, I guess. Okay, so this is our transition matrix for going from one letter to another letter. Okay, and we can now use this to evaluate the probability of a certain decoding, right? So what we do is, so there's going to be a function to encode and decode, right? So we're going to have a decode function, which basically just takes, you apply the text that you want. The decode function, you're going to take the encoded text and the mapping, right? And so basically, we apply our mapping to basically coded text. And then, it's going to output the quote decoded text. Decoded text will be output. So so maybe you have XKX. This is your encoded text, and then maybe the decoded text will be mom or something like that, right? Yes. Question.
Is the length of the text all that is really important for getting a good transition matrix, or would you want several authors?
Yeah, I mean, you can have several authors. It doesn't matter. You just want something quote representative of the language that you're trying to decode to, right? So, War and Peace is just conveniently very long, okay? And so we expect the thing to be somewhat representative of the English language, okay? But yeah, if you wanted to just take random articles from Wikipedia, that probably would work also, and things like that, all right? As far as reference things, okay? So I mean, this could be decoded if in the mapping, if the mapping says, X goes to M and K goes to O, right? But you could have another mapping which says X goes to B and K goes to, I don't know, something else, okay? J, for example. And then your decoded text would be BJB or something like that. And then we want to know, okay, which one of these is more likely, right? Okay, and I think we would say, okay, mom is more likely than this as a possibility. So to evaluate, which probability, the probability of the mapping, okay, we want to find what we're going to do is we're going to deal with log probabilities because log probabilities allow us to add things. So what we'll do is we're going to just look at each letter combination and we go, okay, we're going to go from M to O with, we'll say this is mapping 1 and this is mapping 2. Okay, so for map 1, we're going to say, okay, M to O, we go to our transition matrix over here and we say, how often does M to O happen? M followed by O, you get some number here, right? So maybe a transition dot probability matrix, and I want to find M followed by O. Okay, and it says, okay, that happens with basically a probability of 0.107 type of thing. So this, happens with probability, 0.107. And then we go, from O to M, and then I guess M to blank, right? Okay, and then we say, okay, the probability here is going to be transition matrix from O to M, 0.058, and then we want M to blank, okay? I guess we'll just do 27, okay, and then we get 0.214, right? And we'll we'll do the logs of these and we add them up, okay? And then so basically the probability will be basically the sum of the log probabilities type of thing, okay? Our log probability will be equal to the sum of these log probabilities, okay? With map 2, we basically do the same thing and we say, okay, after it's decoded, what's the probability of going from B to J? What's the probability of going from J to B? And what's the probability of ending with B, okay? And so if we look up B to J, okay, we say that happens with probability 0.005, okay? J to B happens with probability 0.0038, and then we have B to blank character, 0.008, okay? Okay, and then, the log probability here, again, would be the sum of the log probabilities. So we apply a decoding function, which basically just says replace each letter with the appropriate mapping, and then go through that decoded string of text and figure out the log probability of that text. And then when you figure that out, then come back and give us the log probability. Okay. So basically, Decode will just take a mapping, okay, and it just looks up the kind of the character in each of these things and undoes it. And then to find the log probability, basically it's going to look up the letter. If your current letter is one of the letters, it's going to say, okay, take the log probability where we start off with 0, and then you're going to take the current value and then look up the transition matrix of the last letter to the current letter. We're going to just basically look up that combination, whatever that probability is. We take the log of it, and then we add that to the current log probability, and we get this. Okay, and we just do that for all of this, and this is to evaluate the log probability. And so here is our so we can so basically we have what we have to run this. Okay, and so here our text will be a line from Hamlet. Okay, enter Hamlet, and Hamlet says, to be or not to be, that is the question, whether it's tis nobler in the mind to suffer the slings and arrows of outrageous fortune, or to take arms against a sea of troubles. Okay, so we do that, and then we're going to just randomly scramble the text. Okay, and so our coding, our mapping will be, we can just take a current mapping, and it will look something like this. And if I take the text and I code it, and in this case, what we have here is our coded up text. So every time the letter E appears, it's replaced with the letter A, and then N is replaced with a K, and so on and so forth. Okay, so this is Hamlet is JRM now. Okay, and we're going to just start off to run our algorithm. We'll start off with another random mapping. Okay, so mapping, this is just another random mapping. So here's our random mapping. If I apply the current mapping to decode, right, this is the resulting text. Okay, this does not seem to be much better, but we can ask, okay, what is the log probability of my current mapping, and what is the probability of, kind of the current decoded thing, right? So we can ask for this, and so we're going to do that. So we'll say the current decoding looks like this is what the current decoding is, and we can ask what is the log probability. So we apply our log probability function, and it says, okay, the current probability of this is -965. This is the log probability, so it's pretty low. Okay, and so what we're going to do is we're going to propose a two-letter swap. So I just say take a sample from 1 to 26, select two numbers, okay? And those will be the two letters that I swap. So if I choose, numbers 5 and 15, I'm going to swap E with, P, okay? And we'll try that swap. And what we do is we apply, so we say the proposed mapping is going to be equal to our current mapping, except the proposed mapping we have swapped these two letters. Okay, so we do that, we swap the two letters, and then we say, okay, if we swap those two letters, then under the proposed mapping, what will our decoded text look like? Okay, and all it does is it just switches out two letters, and it's going to have something that's completely gibberish still, except maybe now instead of all of the X's, we now have a different thing. Okay, and then we say, okay, based on that, let's look at the probability of this proposed unmapping. Okay, and then we either accept or we don't accept it. Okay, and this is where the Metropolis algorithm comes in. What we do is we say, okay, we compare the proposed likelihood with the current likelihood. Okay, and if the proposed likelihood is we take the difference between those, and if it's bigger than this, bigger than 0, okay, then e to that will be will always be less than this, right? So if the proposed likelihood has a higher value than the current likelihood, then this will be positive, and e to this thing will be greater than 1, and so this will always be smaller. Okay, this is kind of, this is like a little shortcut of the Metropolis algorithm here. And if it's less than 0, there's still a non-zero chance of accepting that probability. It's just going to be lower. Okay, and then if we accept it, then we say this is going to be my current mapping, and otherwise, we reject it. Okay, and then we update our maximum log likelihood if it updates, and then I added this line to kind of track our proposed likelihood. Okay, so here it says we'll run it through 2,000 iterations. Maybe I'll just do 1,000. Okay. All right. So I think this part, I don't know. Can you guys see the? So it starts off like this, and what you'll see is after every iteration, it's going to print out the current translation here. Okay. So we run through it. Okay, and it starts off like this, and it's all gibberish except it's saying like, okay, so here are some things where it looks like it's a little bit better. Okay, and you can start to see the things start to look a little bit more and more like English, right? It's not really English, okay, and it's not completely successful, but then at a certain point you're like, oh, now we're getting some pretty good results, right? We got enter hacklet to be or not to be. That is the question. I mean, this is it looks pretty good, and again, because it's the Metropolis algorithm, even if it's a bad proposal, it will still accept it with a non-zero probability because it's trying to kind of explore certain things. If we only accepted it if it was a direct improvement, then there's a chance we get stuck in a local maximum. Okay, but because it's so it can't make up its mind because apparently the letter L comes after the letter M pretty often, and the letter L comes after the letter P, and so it goes between Haplet and Hamlet and Hacklet and things like that. And it's not quite sure what to do over here, so it gets the question with a C and things like that. But I mean, this is pretty impressive, right? So this is after it seems to it's right here, right? And it's getting the D and the G, it proposes some swaps and things like that there. Okay, and so this is just taking some proposed things, and it's just swapping some letters. And it's not necessarily, at the end of 1,000 iterations, it's not necessarily going to have the perfect algorithm or perfect mapping. However, probably among those that have been proposed, one of them will be pretty good. And a lot of again, the Metropolis algorithm is a sampling. It samples these areas of higher probability, right? And if you think about the entire space of possible solutions, there's 26 factorial possible solutions, but only some of them have decent probabilities, okay? And so the Metropolis algorithm is going to keep sampling from those with higher probabilities and avoid areas that have zero, close to zero probability. And so this is not, oh, it's still going here. I'm going to just go ahead and click stop here. So it's not going to necessarily say, oh, I have found the perfect algorithm and I'm going to stop, but it's going to keep sampling areas that are pretty good. And at a certain point, you can probably say, okay, we've reached a point that's pretty good. And so I just kind of want to give you a plot of this is the log probability. So in the beginning, it accepts only every swap that it does, it's like significant, and then at a certain point this is kind of where it kept stalling. So after around 200 iterations ish, the proposals didn't necessarily improve the log likelihood, but in the beginning, it did. Let me just here. Let's go back and let's just do 200 iterations and just kind of see. We'll do a mapping here, 200 iterations, and we'll do this. Okay, let's just run through this again. So, this is all gibberish, but again, it's just trying to find letter sequences that look more reasonable than complete gibberish, right? So, we're gonna have it end at 200 iterations, which it's not perfect here, but but it seems if we combine this with the method proposed in the other algorithm with a lexical database. So this is at the beginning where it's just complete garbage, and then you propose one letter swap, and I don't even know which letter swap they proposed, but I can't tell. Huh? Okay, yeah, the C and the K. So apparently these is more likely, and certain letter swaps, it says, oh, okay, this. So as soon as we did this, now we start to get things that is still not a real word, but this looks more like a real word than something before. Okay, and as it goes, it gets better and better. Okay, so anyway, this is one application of kind of all of this slogging through that we've been going through in terms of Monte Carlo and Markov chain stuff that we've been doing. Okay, so we'll end here for today, and we'll continue on Wednesday.